Ready? All right. Hi, guys. Everyone. Here we are. You know, just getting a little construction work done.
Working for the man.
Exactly. Hey, you got to put in that overtime in the summer.
You know it. You know it. All right. Well, today we're going to be talking about something called calorimetry. So calorimetry is a way to study how much energy is in something by how much heat it gives off.
All right.
Or absorbs. So that's kind of what we're going to be studying today.
Okay, I can do that.
Pretty straightforward.
Because, you know, it's hot right now. We're in the construction zone. It's summer, the 5th season of Chicago construction.
Construction season.
Yep. Yeah. All right, here we go.
All right, so just an overview. When we measure the temperature change in something, that's the energy change.
Okay.
Right? So if something gets hotter, if it increases temperature, it has more energy.
Okay.
If it decreases temperature, it loses energy.
So like right now versus when I'm really start to work and I get hot and I sweat.
Yeah, right when you're about to pave the road back there in about, 30 minutes or so.
Exactly, yeah.
Yeah.
So getting a little steamroller.
That's exactly right. So there's two main reasons why we use calorimetry. The first one is, let's say we have something hot or something cold, and we want to know how much energy is in there.
Oh, okay.
We can use calorimetry that way.
Okay.
And the other one is, let's say we do a chemical reaction, and the reaction gets hot or cold.
Oh.
And so we would use calorimetry to figure out how much energy was released in the chemical reaction.
So like kind of like those ice packs when you pop the thing in the middle and...
Exactly. We can use calorimetry to figure out how much energy the ice pack is absorbing, because it's getting colder, it absorbs energy.
Got it. Cool.
All right, so a couple things to note. Heat is just kinetic energy.
And kinetic energy is the energy of motion. Okay.
Yep, that's right.
Yes, that was a great robot.
So hot things move faster.
Right.
Okay, so, and cold things move slower.
All right.
So when you stick your hand in a pot of boiling water, thank you for the sound effect.
You're welcome.
The water hurts you because it's just moving faster. And when you stick your hand in a pot of ice water, did not hurt. I appreciate that sound effect. The water's physically moving slower, so it doesn't have as much energy and it doesn't hurt you.
And the way you can kind of remember that is like if you put your hand in hot water, you're going to pull it out really fast because it hurts.
Exactly.
Cold water, you're like, meh.
I'm good.
Yeah.
All right. So if something gets hotter, it's absorbing energy, and if it gets colder, it's releasing.
Got it.
Right. This is the apparatus that we're going to be using, something similar like that to calorimetry.
Apparatus, otherwise known as thingy.
Thingy, yes, yes. Couple of thingies to note. The apparatus, or thingy, it's just two styrofoam cups nested inside each other, and that's because we don't want any heat or energy to go in between. And then we do all of our reactions in water because it's really easy to measure the temperature change of water, and water is not hazardous, and it's super cheap, and it's super safe, and it's just a fun thing to work with.
I like it.
Yeah.
So, and instead of a thermometer, we might be using a probe. It's a little easier.
That's right, and a little more accurate, too.
Yeah, so.
That's how we roll. All right, so a couple of important things to note is that the energy gained by the water is what was lost by the object, or vice versa.
Oh, okay.
Energy has to be conserved, so we're never going to create or destroy energy.
Can't make it, can't break it.
Boom. So we can just transfer it from the object to the water, or the water to the object. So by knowing how much energy or heat the water changed, we can figure out how much heat or energy the object gained or lost.
Pretty easy.
Yeah, pretty easy. And that is represented by, oh, it's not represented by an equation. Never mind. That's coming up. So...
Stay tuned.
Yeah, I don't know where my animations are, apparently. Okay, another important thing to note is specific heat. Specific heat is just how quickly something heats up or cools down.
All right.
Right? Like, let's say you're walking along the beach on the summer, and that sand is rippingly hot, right?
Yes.
That stuff gets toasty.
Yeah.
That's because sand has low specific heat. Doesn't take a lot of energy to heat that sucker up. And you're like, oh man, my feet are really hot. I'm going to jump in the water to cool down. And that water is like 35 degrees.
Yeah.
Yes. Because water has a high specific heat.
So it takes longer for that to get warm, right?
Water has one of the highest specific heats. That's why it takes so long to boil a pot of water. Whereas if that pot was empty, that thing would get pretty hot pretty quick.
Very true.
Yeah, so.
All right, moving on. Heat. But it's not represented by the...
That's very hard to represent sounds. Yeah.
Yeah.
So our actual heat equation, here's where my equation came in, is Q equals MC delta T.
Delta.
Delta.
Shout out to my sorority sisters.
Tri-delts. Woot. Woot, woot. I like to call this MCAT because the delta looks like an A, and then it's MCAT. It's fun thing. So Q is heat. We measure heat in joules. Just a measurement of heat. Don't worry about it. You'll talk a lot about it in physics. M is mass, works out well. It's in grams. C is specific heat. And they use C because they're starting to run out of some letters, so they just tossed it in there.
And those you'll get in a chart. It's specific to everything.
Always given, yes. Every substance has a different one, and they're always given to you. The units are funky. That's just so the math works out. Don't worry about it too much. And then delta T, delta means the change in, so delta T is the change in temperature.
So you subtract the starting from the ending. Or the ending from the starting.
How much it changed. You'll
got
see. It's really super duper easy.
Let's rock.
And roll. All right, last but not least, like we said before, the energy of the water is going to equal the energy lost of the object. Okay.
So technically you could put a plus sign in front of the water, right?
I can. Watch. Check this out. Okay, so I've been practicing with my stylus.
Ooh.
I'm going to change it to a pen, and
boom!
Whoa,
wow!
That is a fantastic plus sign.
You've gotten really good.
This is harder than it looks.
So anything that is absorbing, the other thing would have a negative sign, right?
Exactly. Plus means it's absorbing heat. Minus means it's losing heat.
All right, I can handle that.
Okay. All right, so we have a little sample here. Yes. Sample of iron. So we took a block of iron, we heated it under a Bunsen burner, because why wouldn't you? That's what we do. And we dropped it into 100 grams of water. Fun fact, a milliliter is a gram, so 100 milliliters is 100 grams.
Oh, that's pretty easy to remember.
All right, so the water started at 20 degrees Celsius, and it ended at 25. So it went up 5 degrees.
Okay.
It says how much heat was in the metal block. So we like to do a couple things here. We like to, first off, circle our unknown.
Right.
What are we looking for, Ms. Keiser?
Heat.
Heat. Ooh, that's a rough circle.
Yeah, that is.
You know, it's a little brutal.
Yeah.
And then we like to underline what we're given. What's one thing we're given?
We definitely got the mass, because I know that grams is representative of mass.
Yep.
So there's 100 of those. And then we have the change in temperature, so we went from 20 to 25.
Perfect. And so our change would be 5.
Yes.
So we're going to use our MCAT equation.
Okay.
We don't know Q.
That's what we were looking for. That's why we circled it.
Yep.
We got the mass, which is 100 grams.
Great job.
Because G, mass, they go together. Okay, specific heat of water. You looked that up on the chart.
Yep.
Okay.
Always a given to you.
Yep. And then the change in temperature, which we did again, 20, 25, subtract 5.
Yep, exactly right.
Okay.
All right. So here we have all of our variables listed. So let's do it and see what we get.
Now this is the plug and chug part, right?
The plug and chug. So we know heat is MCAT. We know mass is 100.
Okay.
Ooh, these are rough numbers.
Yeah. 4.18 for the C.
And then our change temperature is 5.
So you're going to multiply all those together.
And we're going to get 2,090.
Ooh. And that's in joules.
That is in joules.
And you'll know that because you'll cancel your units out and all the business. We'll talk about that later. That was very good.
You like that?
Very good. Okay.
I think it adds a panache.
Yeah. So this is a positive number, right?
Yes, because the water got hotter, right?
Okay, so the water gained the energy. So if we were to look at the iron, it would probably have a negative 2,090 joules.
It would have exactly a negative 2,090 joules.
All right, I get this.
Energy is conserved.
All right, cool. Try one more?
Let's do one more.
Okay.
So here we have NaCl, table salt.
Okay.
Dissolve it in 10 grams of water, and the temperature of the water dropped from 25 to 23. So it actually got colder this time.
Oh.
How much heat did the water transfer to the NaCl?
Oh. Well, we're still looking for heat.
Yep.
So we're going to circle that, right? So we're going to...
I'm going to...
Circle the heat.
Circle the heat. There's heat. Okay, we're going to circle heat.
Okay. 10 grams of water. And then we got 25 and 23, and when we subtract those, it's a negative 2.
It's a negative 2. There's a little typo there. It's a negative 2.
Because it's always the final from the initial.
That's right. Because it went down in temperature, we have to have a negative temperature.
All right, let's plug and chug this bad boy.
Alrighty, so...
Oh, so now we're going to use our...
We're going to use our MCAT equation, right?
Right. Q equals MC delta T.
That means Q is going to equal
10 times 4.18.
4.18
times negative 2.
Let me fix that over here so there's no confusion.
Okay.
Because it went down in temperature.
Right.
In this case, Q is going to equal negative
80.36
joules.
Oh. So now it's a negative because the water lost heat and the sodium chloride gained the heat.
Exactly.
I
So
get it.
this is the Q value for water. So the water lost that amount. Sodium chloride would be what?
Positive 80.36.
Exactly right.
All right. Well, guys, we got to get going. We got some work to do. So have a good one.
See you later.